All right, so last time we were talking about plasticity, and we derived this sort of general scalar framework to do plasticity return algorithms for J2 plasticity models. And we worked through all the details for an isotropic hardening model. And at the end, I told you the isotropic hardening case is really one of the very few when we can actually write it down what the stress should be in closed form like that, right? So let's sort of go to the next, maybe the next most complex constitutive model, and this would be a model that's viscoplastic. So viscoplastic implies, visco implies that there's a rate dependence. So schematically, we'd have stress strain curve that the hardening portion of the curve would be a function of strain rate. So typically it would increase as a function of the plastic strain rate, okay? And so a hypothetical yield surface for a model like this, so our yield surface would be the square root of 3 halves S, right, according to what we did last time, minus the quasi-static yield stress, so this point right here, times 1 plus beta times the strain rate to the nth power, okay? So beta and n would be basically fitting parameters for this constitutive model. So you'd have some real stress strain data that you collect in the lab, and then you could fit this model. You could choose a beta and an n that would fit the family of curves best as possible. Right? And so if you remember, we had this complementary condition that f dot must equal to 0, right? So let's if we compute that, right? So if we compute f dot, we have the square root of 3 half s dot minus n beta that. Now we're going to substitute in our flow rule, or associative flow rule. Well, this is equal to 0. And so if we solve that for s dot, we get this guy. And then if we plug this back into, remember in the previous notes we had this equation star. It was a scalar equation that we derived from the additive decomposition of strain rates. So just look back in your notes and we labeled equation star. So if we plug in s dot into that equation, and we get this equation. right? And so the only unknown in that equation, everything else, I mean, this is, I think I used this symbol, epsilon d. Right, so this is an input, right? This is what's driving the equation, right? So this is known. This is a strain that's driving the thing, this plasticity. So this is known. This is a material constant, material constant, material constant, material constant, material constant. So the only unknown in this is lambda, which is, or the function lambda, but it's clearly a differential equation, right? Not only that, but a nonlinear differential equation. And so, so whereas before, when we did isotropic hardening, we could solve explicitly for lambda dot, right? Plug that back into the flow rule, back into the constitutive equations. Can't do that here. We can't solve explicitly for it, so we have to solve this numerically. Right? So we'd have to solve this numerically for lambda to then update the plastic strain and put it back into the constitutive equations. And this is just sort of the next most complicated model we could have with rate dependence. Believe me, they can get far more complicated than that. So